like, okay, I see you have tried. Let me figure out if you got the problem. Let me figure out if you got the problem. That goes for everyone. I like that goes for everyone. I want to see that you have tried. Like, I don't want to just you come to me and be like, hey, I don't know what to do. Like, how do I start this problem? Like, how do I start the problem? Go and watch the videos and you should have an idea how to start the problems. But once you start, like, if you show me what you're doing, if you show me what you're struggling, and I see you have tried, I'm happy to sit down with you until we figure it out.
I'll remember that in future, because I normally start early. As soon as they come out on Friday, by Saturday I have to start working on it, because it's a lot of information and I have other classes, so I don't waste time at all, so that in case if there is anything. And when you said I should be careful about using the mesh, that was very helpful, because I might reach a super mesh and that would be an issue. So that was a very good hint for me. Yeah. So thank you.
Yeah, no problem. Okay, so now that more people have joined, like as always, if you can start turning your cameras on, we will start in a second. So I see there is actually a little bit more people here than on my art class, but I have noticed that attendance to these check-ins kind of keep going lower and lower and lower and lower. And I know it's not mandatory. I know it's just like recommended, but it's like highly recommended. I tried to give a lot of like hints as we were talking with Claire. I tried to give like hints of like common mistakes and things. So I just ask you like, try to keep coming if you're struggling with something, or like if something happens 1 week, like I understand, but for the most part, like I'm just here for you. Like I wouldn't be doing this if it wasn't because I thought I could help you somehow. So yeah, does anybody know if there is midterms, or like, do you have any big assignments this week? On my other class, I only have 3 people showing up today out of like 100 and something. Yeah, it was really bad. I was really sad this morning being like, why is nobody here? So I'm glad to see there is like a few of you here. So yeah, does anybody know? Is there exams, homework? What's going on this week?
I personally have like 8 assignments due today specifically, and like a couple midterms and other ones after that. So it is kind of difficult to attend these, but yeah, they're important.
Thanks for letting me know. At least I know now that there is like things going on, and it's not just like, I don't know, people is not coming.
People just don't feel like going.
Yeah, that's fine. I understand you have a lot of other things, but I'm glad and happy that you all are here. Someone is saying I have 2 quizzes and 2 homeworks. 1 quiz is 10% of the final grade exams. Yeah, okay. Well, I'm glad you're here. And again, these are just meant to help you. I'm trying to record them, but I feel like these sessions are only helpful if I have people, because if I only had 2 people like, or 3 people like this morning, like nobody's asking questions. So they're like, I don't know what to talk about because I don't know what you all are struggling with. So I don't know what to try to help with. Someone is saying that they have a question. If you want to ask your question now before I start, I can try to answer it. If it's relevant for everyone, you can put it on the chat or you can ask out loud, whatever you prefer.
So,
yeah.
Okay. So I was looking at problem 1, and so I can't figure out how to, like, I don't know. I have it started and I have it like, I have my voltage source pulled out, but then how does it work with the current, I guess? Wait, sorry, go to another question. I think I'm asking about like a different problem.
Okay.
Sorry about that.
No, you're good.
Would I be able to ask my question?
Yeah, let me figure out. All right, well, the other person. While the other person is figuring out, the person that just asked if they can ask a question, can you ask your question now?
Yes, it is me. Do you hear me?
Yes.
Perfect. I have a question about homework question 1. I do not know if I did it right, but I went through.
Can you put your microphone closer to you? Like you're really far away.
I got you. Let me change my microphone so you could hear me uh, better.
Hello? Yeah, I still can hear. Ashley, do you have your question? Well, yeah, I heard he was switching his mic, but
Okay, so yeah, okay, so it is about question 1.
okay.
I mean, no, 3. I can't count today. Okay, so I've removed I'm guessing you have it in front of you, right?
Yeah.
So you can like see what it is. Okay, so first of all, so I removed all of my sources, and then with this, these 2 resistors are connected to one node right there. Is this helpful, or should I join on my iPad too and share my screen?
I can see it. Can everyone see what she's showing? Yeah, everyone can see you, I think.
Awesome. Okay. So then these are connected in parallel. So then when we combine them, did they get like shorted out in the end because they're connected to this, like each end is connected to the same node? Okay, awesome.
They're not connected
And then
they're connected in series. But yes.
What?
They're connected in series, not parallel.
Wait, they're not.
Because to be in parallel, they need to be, well, they're connected in parallel and series. So it depends on how you are simplifying. Because if you are simplifying parallel, then one node is connected to nothing. The way you simplify it was like if they were in series. You simplify them and then they were connected to the same node.
Okay. But I guess then, like, regardless of how I simplified it, though, it would get shorted out.
Yeah, it will get removed. Yes.
Okay, awesome. And then another thing, so I didn't keep my voltage source in. Am I supposed to do that? Or
okay.
No?
So that's a good question, but then I'm gonna share my screen and
okay, awesome.
I'm gonna try to talk about it. So iPad, share. I'm gonna open my chat so I have it on this side. So if you have any questions, I see it. Everyone can see my iPad now?
Yes.
Yeah. Okay. Let me put this bigger so I can see all your faces. Cool. And I actually have to record this, so record on this computer. Okay. So I guess the questions are about like Thevenin and Norton and like how we remove things. So when we are talking about that problem is asking you about Thevenin equivalent. So what you need to remember is that every time they ask you for the Thevenin equivalent circuit, you have to do 2 things. The first thing is that you have to find the Thevenin resistance. And then the second thing that you have to do is that you have to find the Thevenin voltage. Now, when we are looking for the Thevenin resistance, let me open a random example here from last semester. This one has a problem. You just need a random circuit. Here we go. So I have a circuit that looks something like this. Plus, minus, there is a 1 ohm resistor here. There is a 3 ohm resistor here, 1 ohm resistor here. This one actually has a current source. Then there is another 3 ohms resistor here, and then your load is right here. So if we're gonna find the Thevenin equivalent, you always have to think about, we are finding the Thevenin from the point of view of the load. So if you are finding the Thevenin equivalent resistance, there is 2 things that you always have to do. So the first one is that you remove the load. And then the second one is that you turn off all the independent sources. So when you do that for this circuit that I just drew right here, if I do copy paste, and we are doing part 1, what I do is I'm going to remove my load. And I always want to make sure that I don't lose the 2 points that we are going to find the equivalent from. And if you remember, like last week, during this weekly check-in, I did kind of an example about finding equivalent resistance. And I was pretty repetitive about, like, be careful, you are finding the equivalent from 2 points. Don't lose your 2 points. Those 2 points can change. And I was trying to be intentional because I knew you were gonna need that for this module. So in this case, like, make sure that you label which 2 nodes your load was connected to, and that whatever happened, you don't lose those 2 nodes. Then the other thing that we have to do is that we have to turn off all the independent sources. So how do you turn off independent sources? So remember, the current source becomes an open circuit, and then the voltage source becomes a short circuit. So I can put a short right here. Now, when you are looking for the equivalent, you are looking from the point of view of the load. So you are trying to simplify without losing point A and B. So then what you were saying is like, well, I turn off my voltage source and my current source, like my what? Well, by looking at series or parallel, eventually this circuit is going to become one single resistor, and this is what we will call our Thevenin equivalent resistance. However, when we are going to do part 2, which part 2 is find the Thevenin voltage, we are gonna go back to the original circuit. So you don't find Thevenin from this circuit that you did the equivalent resistance for. You go back to the original circuit to find the Thevenin voltage. Does that make sense?
Yeah, sorry, I'm muted. I think that makes sense. Okay. Sorry if I'm just repeating this back to you, but so I set everything to 0, like each individual source to 0 to find the equivalent resistance, right? The Thevenin resistance.
Yes.
And then
by looking at series or parallels until you're gonna get one single resistance.
yeah, and then how do I find the voltage again?
So then part 2 will be to find the Thevenin voltage. What it says is that one more, you're going to remove the load. But now instead of, you're gonna remove the load, and then you're gonna, I'm trying to explain this in a different way. Your Thevenin voltage will be the voltage difference between the 2 nodes that the load was connected to. So if this is my original circuit again, and I'm trying to do part 2, what I can say is that I'm going to remove my load. So we'll be take out this resistor right here that was the load. And now I'm going to label A and B, the 2 nodes that the load was connected to. And then if you find the voltage at node A and the voltage at node B, your Thevenin voltage is just the voltage difference between those 2 nodes that the load was connected to. So this will be V of TH is equal to V of A minus V of B.
So then how do you, okay. So then I always mess this up too. How do we deal with the current source in there?
All right, so on this particular example, I know Rachel is saying that just a question, but let me finish here and then I will answer, and Maxine also. So I will get back to you. I see you is all that I want to say. So Thevenin voltage. So the first thing on this particular example that you should be able to see is that this resistor is on an open circuit. So you will have to remove that resistor. Yeah, because there cannot be current going across this resistor right here. So this circuit will get simplified as this resistor right here is gone. And these are the two nodes that you are trying to find the voltage across. So in theory, you are just trying to find the voltage across the voltage source. So don't get confused, because I think this was a confusion also on the previous homework, or maybe it's this homework. No, I think it was the previous homework. When I was asking to find the power for a current source, you cannot forget that voltage sources also have a voltage, because the voltage across the voltage source, once more, is just the voltage difference between the two nodes that current source is connected to. So if you are doing, based on what we talked about last week, which technique will you use to find this voltage VTH?
Okay. Yeah, I didn't do so well in the homework last week.
Fine. So that's the technique that we talked about
mesh
last week.
current analysis?
If you do mesh current analysis, you're going to be finding the mesh currents. In this particular,
Okay, so it'll be node voltage.
like a lot of the time, it depends. It isn't just depends on what you are trying to find, but it also depends about like what do you feel is easier. Like if you do mesh current and what you are finding is a mesh, the current and a mesh, and you don't know what to do with that, then don't do mesh current analysis. In this particular example, think about what I just told you right here. I told you the Thevenin voltage is just the voltage difference between the two nodes that load was connected to. What we know is that if we do no voltage analysis, the no voltage result or the no voltage solution will be the no voltages. So if we do no voltage analysis, how many nodes does this circuit have?
This circuit has 4 nodes.
Yeah, it has A, B, maybe another one here, and another one here, D. If we do no voltage analysis, we are going to know the voltage at all the nodes, at A, B, C, and D. So if we do if we do the no voltage analysis, once we find what VA, VB, VC, and VB are, we can just say that VTH is VA minus.
So then, so with node voltage analysis, we have to set something equal to, we have to choose a reference node and like set that to ground, right?
Yes.
So then, so I guess like if I were looking at this, I would pick node B to be set to ground.
Yes.
So would that mean that our Thevenin voltage would just be VA?
Yes.
Since we're setting VE to ground? Okay.
I know there is at least 2 people that have question about this. Who wants to add the
question? Like, I know like I wasn't first, but in this example, you said that the resistor, like right before A, is on the open circuit, which I understand, but like in reference to problem 3 specifically, is that like always true? that like a resistor, like if you look at problem 3, once you remove the current source and make that an open circuit, would the 20 ohm resistor also be an open, or sorry, because it's, when you're not removing it, would it also be on the short circuit or no?
Okay, that's problem 3. Let me get back to you.
Okay.
Okay, let me get back to problem 3. Rachel or Ethan, what question did you have about this? Or if it was about this?
My question was about question 3 as well.
Okay, so we'll get back to you too about question 3.
Wait, so does this apply to question 3, what we've been doing?
It kind of do, but what they're asking, I think, is related to what you mentioned at the beginning about the resistor being without connected to a node. That it's a different question. Now, does anybody have questions about this particularly? Okay, so if you don't have questions about this, the main thing that you should take about this is when you're finding that I'm gonna just be repetitive here because this is a common mistake and it's kind of related to something that they were just asking. So when you are looking for the Thevenin equivalent resistance, if you look at these two resistors, it looks like that on an open circuit. Those resistors are not removed because on this circuit, there is no voltage or current source. So in this particular example, it doesn't matter that these two are on an open circuit because we are looking for an equivalent circuit and we care about this point A and B. On the right side, when we are looking at this circuit that has voltage and current sources, this resistor can be removed because there is no current or voltage on an open circuit. So when the voltage and current sources are on, we know that the current here is going to be equal to 0, so that can be removed. Is this clear for everyone?
So current can't flow in that mesh specifically because it's open.
Yeah. So the current cannot flow across that resistor. What that means is that resistor is acting as an open circuit. It's acting as a short circuit. So if I consider this to be node E, I know that node E and node A are going to be the same because if current across the resistor is 0, voltage across the resistor is 0, so that is equivalent to just having a wire.
Why is there no like voltage that goes through there though?
Because voltage is equal to current times resistance. And if current is 0, then the voltage is 0.
Why is the current 0?
Because current needs a closed path to flow. Current, if I'm the current, I have to be able to come back to where I started. And if I am the current going across this 1 ohm resistor, when I get to this point, it doesn't make sense for the current to go across this resistor because it doesn't have a closed path to keep going. That's why if the current is coming across this 1 ohm resistor, it will have to only be able to do something like this. It needs to be complete path for the current to flow. Okay. So in this example here, if you go across this resistor, once you get to node A, you don't have anywhere to go. So that's why the current across that resistor is 0. During Ohm's law, the voltage across the resistor is 0. So the resistor can be replaced by a short circuit. Okay? I'm going to go to problem 3. I know where the confusion is, and all of you that have questions, you can ask. So there is, I think this is the part that was creating a confusion. It's not exactly the same, but it's something like this. I'm just missing one resistor, I think. So the problem here is this part right here. And that's what I was saying. There is two ways you can look at this. And either way, you're gonna get to the same answer. So the first way that you can look at those two resistors, it's like if they are in series. And the reason why they are in series is because you can think about, well, there is one single path for the current to go from this point to this point. When we think about a series, if I have a node A right here and a node B right here, I know that the equivalent of my series will have to be connected between node A and B. And if I assume that that is a series and I simplify it, now it will have to be connected between node A and B. But when we look at this particular example here, I should have drawn it smaller just so I could talk and show you at the same time. Oops. So if you simplify it as a series, what you know is that your equivalent will have to be connected between the same two nodes A and B. But on this particular example, when we look at the nodes, it looks like this node A and B are exactly the same node. So that's why I forgot your name. And I don't have my pen here. Okay, your classmate was saying earlier, where now this resistor is going to be shorted out because both nodes, this resistor is connected to exactly the same two nodes. So if you have a resistor connected to exactly the same two nodes, once more, when we look at the voltage for that resistor, we know that the voltage across the resistor can be written as the voltage difference across the two nodes that the resistor was connected to. But if A and B are exactly the same, then this is going to be equal to 0. Yes? So this resistor right here can be removed. Is this part clear? Now, the second way to look at this is I can look at this as a parallel. And the reason why I can look at it as a parallel is because since I already know that node A and B are exactly the same, if I consider this node right here, node C, I know that both of those two resistors will be connected between node A, B, and then node C. Yes? Now, if I redraw my circuit with this new idea, it will look something like, it doesn't matter which way, but it will look something like this. Where this is just the parallel between those two resistors. Yes? Now the problem here is that, or it's not a problem, but like the trick and why it kind of like relates to what we are doing before is that I'm trying to find the equivalent between node A and B. I'm not trying to find the equivalent across C. Node C is not of interest for me. All that I care about is node A and B. So because node A and B are the one that I care about, and this node C, like I don't care about it, it's almost like you're gonna be finding your equivalent, and you can make it look something like this is your RTH, and then there is a node C right here, which this will be the same resistor. This resistor right here is not affecting your Thevenin equivalent resistor. That resistor is just connected to another node that we don't care. So that's why in this second example, you also will be able to take that resistor out. So it doesn't matter whether you consider it to be in series or parallel, in both cases, that resistor is not going to affect our answer. Does this make sense? Does this answer the questions about problem 3? Or what are questions you have about problem 3?
I had something different pertaining to problem 3. Simply trying to find the Thevenin like voltage. I understand that it would go like you're finding the voltage difference between A and B, but my question was because similar to what we were talking about previously, in the 20 ohm node at the very top, that would not short circuit. There's nothing that's going to be an open circuit here because they're still able to have current flowing in through it, right?
Yeah, that one is fine. I'm gonna do a drawing here since I cannot show my solutions because they have, or the problem because they have my solutions. But yeah, when you have your circuit, it looks something like this. Sorry, I'm drawing this as quick as I can. So you are trying to find the voltage between these 2 points. That's the only like trick that I can give you, or like clue. Be careful that I am saying assume the load has been removed. So the load has already been removed. So when you are looking for the Thevenin equivalent voltage, in theory, all that you are looking for is just the voltage across this 60 ohms resistor. If you find the voltage across the 60 ohms resistor, you already found your Thevenin voltage. So yes, this resistor up here, it's fine because there is a still like current can go this way and this way, and then there is current coming this way, which will go down. There is closed paths everywhere. You can start here and go around, come back. There is a closed path. So that one is fine.
Remove the load when finding the equivalent resistance, though, correct? That's not included.
They're telling you that the load has already been removed. So even when you are finding your Thevenin equivalent, that's why I left this resistor right here. This will be your 60 because they're telling you the load has already been removed.
Oh, okay. So that should be included then. Okay.
Yes. So the 60 ohms resistor should be included for both when you're finding your Thevenin voltage and when you're finding your Thevenin resistance, because they're telling you that the load has been removed already.
Awesome. Okay, thank you.
Anybody else questions about problem 3 or anything else?
I had a question about example 2 for Thevenin equivalence, module 4.
Example what, sorry?
Example 2.
The extra practice problems?
Just the regular slides, like the.
Okay, so it's, I go to the slides. Let me open this. Oops. This is lectures. Is it module 4?
Yeah.
And then which video is it? Which number?
Example 2 of the Thevenin equivalence.
This is superposition.
Thevenin equivalent circuit examples.
Let me try to. So this is their class 2020. I think it's 5. This one, right? Yes.
Yeah. So I guess I had a question further down about the Thevenin voltage.
Yes.
So why was it just like adding the voltage of the 2 ohms resistor and the dependent source. Like I was thinking like a voltage division or.
Why did I added the 2 voltages to find the Thevenin voltage?
Yeah.
Okay, it's because I guess I kind of like skipped some steps, but in theory, what we need is the voltage at node A. Yes, because we know that if I assume VB to be equal to the ground, I know that the voltage at node D is equal to 33 volts. Yes.
Right.
And then I also know that the voltage at node C would be equal to 3 I of X, which I of X, they told me is equal to 3. So I can say that the voltage at node 3 is 9 volts. Yes?
Mm-hmm.
So if what I want is the voltage at node A, because I know that my Thevenin voltage would be equal to V of A minus V of B. And I know that VB is 0, so all that I care about is the voltage on node A. What I can do is I can find the voltage across the 2 ohms resistor, because the voltage across the 2 ohms resistor can be written as the voltage on node A minus the voltage on node C. And the way I can find my voltage across the 2 ohms resistor is by doing Ohm's law, which would be 2 times the current across this resistor, is equal to V of A, that is what I want to find, minus VC, which is 9. So then you just have to move the 9 to the other side, and you get that 2 times I of X plus 9 is equal to V of A, which gives you the 2 times 3. This is 6 plus 9 equal V of A, which gives you 15.
Yeah, that makes sense. Thank you. I think the other source just kind of threw me off.
Yeah, so it's just that the way I was thinking about it is that if I do the voltage across the 2 ohms resistor plus the voltage across that dependent source, the voltage across this resistor is VA minus VC, plus the voltage across the source is VC minus VB. So you can see that the VCs cancel out. So you get the voltage across VA and VB. That's a good question. Anybody else, any other questions about homework or the slides or anything else?
For 1B, what do you mean by 10-foot resistor?
Wait, are we talking about the homework problem?
Yes, for homework 3. I'm pretty sure it's
Okay.
not foot. I think it might be something else, but I'm
Oh
not sure.
yeah, it should be 10 ohms resistor. That's a typo. Yeah, it says find the power dissipated in the 10 something else. Yeah, it should be ohms resistor.
All right, thank you.
Any other questions about anything else?
Yeah, I had a question about 4 part B.
Yeah.
So I ended up getting like a negative current. So for finding the R, the resistor of the load, should we flip the current so it's like pointing down and positive so you can find a positive resistance, or should I use the negative and get a negative resistor?
Yeah, like you. So it just means that the current is going in the opposite direction. So yeah, you should draw the current going down.
Okay.
Yeah. Yeah, so the question was about the last problem. When you have your Norton equivalent circuit that looks like this, if you find that this current has like a negative value, something like minus 0.5, it's not the answer, I'm just giving you a random number. But if it's something like minus 0.5, then what you know is that the current is, you can say that the current can go that way, but if the currents go that way, these two currents are gonna also be negative. So it can be something like minus 0.3 and minus 0.2. I don't know what they are exactly, but they're gonna be negative. If this current is negative, those two currents are gonna be negative. So you just have to be careful that you have to know that the current is negative, or you can just flip the direction of the current and say the current goes down this way, then goes down this way. Now this is 0.5, and I know that the currents going this way will be 0.3, and this one will be 0.2. Because currents can be negative, voltage can be negative, but resistors always are positive. You cannot have negative resistor values. So you just have to be careful when you are finding the load, that is this resistor right here. It has to be one of these two cases. Resistor always needs to be positive. Is this clear? I know Maxine hasn't asked his question. So you can ask that question, and if you want to wait, the only other thing that I wanted to talk about and make sure that everyone understands today is I had quite a few questions about the first problem for superposition. The only thing that I can say is, like, be careful that you are not trying to simplify the circuit as much as you can. When you are doing superposition, you are trying to break the problem. Let me see the example that I was looking at earlier. Homework. Oh, we can even do it for the problem that I had up here. For this one. Oh. If we want to apply superposition to find that Thevenin voltage, that is the example that we were looking for before, what superposition says is that I can break my circuit into two smaller circuits and do the analysis. So the first one would be if I turn off my current source. So if you turn your current source off, what you're gonna get is, like, there is a voltage source. You have a 1 ohm resistor here, a 3 ohm resistor here. There is this one. Your current source is going to become an open circuit. These are your nodes A and B. So what we know is that this resistor is on an open circuit, can be removed. So if you find the voltage across that resistor 3, we know that that would be the contribution of the voltage source to the Thevenin voltage. When you are doing the second part, that is turn your voltage source on, then your circuit will look something like this. Now, what you're still trying to find out is the voltage across this current source, and the voltage across that current source will be the contribution of the current source to the total Thevenin voltage. And we know that our Thevenin voltage would be the sum of both VP and VI. The reason why I'm saying be careful is because I think of one of the videos I said something like, the first thing you should try to do is simplify. And what I saw a lot of people was like, well, I can get rid of that resistor, these two are in series. So now I have a voltage source connected to a 4 ohms resistor. So then my contribution of the voltage source is equal to, let's say this was a 2 volt voltage source. My contribution is just equal to 2 volts. Be careful that this is wrong, because these two nodes right here are not exactly the same two nodes A and B. When you simplify, now this is your node C and this is your node B. So yes, it is true that VC minus VB is equal to 2 volts, but it is not true that the contribution of the voltage source is equal to 2 volts, because what you needed was the voltage across the 3 ohms resistor and not the total simplification of your circuit. Does that make sense? It happens in this particular example that if you go and you simplify, you say these two are in parallel and then in series with that one, when you simplify, it does happen that the voltage across this resistor was the voltage across the current source, but it's not the same. And I have seen people that have sent emails or have come to office hour, they are just simplifying the circuit as much as they can. Problem 1, what it's asking you is to find the voltage across the 10 ohm resistor using superposition. So be careful. Don't simplify as much as you can. Try to pay attention to what you are solving for. What am I looking for? The circle will look simpler, and you should simplify as much as you can without losing the variable that you are solving for.
So
that makes
and then, if that's all right. So in part 1, you said, use the superposition to find the voltage V in the circuit, which is across the 10 ohm resistor. So you would find the contribution that you would find the voltage across when you remove the voltage source. So when it's current, and then you'd find it when you remove the current source, and then you'd add it together.
Yes.
That's it. Okay, perfect. I just wanted some clarity on that. Thank you.
Yes. So you're gonna find, yes. So kind of same idea here, it's just that I'm warning you what is wrong to do. But yes, like the same idea here, what we will be doing is we turn off the current source, we find the voltage across this 3 ohms resistor, then we turn off the voltage source, we find the voltage across the current source, and then we add those two up, and that would be our Thevenin voltage, which on the homework will be the voltage across the 10 ohms resistor. Any other questions?
Yeah, I just want to make sure about the problem 3 you explained. Can I share my screen?
You
Yeah.
cannot show your homework.
Oh yeah, I'm not showing my homework. Yep.
All right.
Okay, yeah. Let me.
Yeah.
Yeah. So this is the one you explained just now. So it was the isolate as in series, and then you said this will be shorted out, right?
Yes.
And then will this be like in this circuit, or like this whole series will be like the shorted out? So only 60 ohm remains.
Okay, let me go back to my screen. Let's see it.
Okay.
So this is the part that your classmate is asking about. So
Yeah.
after we said that this thing is shorted out, then our circle will look something like there is a resistor up here. There is this one right here, and then
Okay.
yeah, I got rid of that resistor in the middle. Now, how many nodes does this circuit has? So all of this right here is
One and
one
two.
node. It would be node A,
Uh-huh.
and then all of this right here would be another node, which is node B, and it's
Yeah.
still of interest. Are these
Uh-huh.
two resistors in series or parallel?
They are parallel.
Yes, they are in parallel. So you can just find the parallel between those two.
Oh.
It will look something like this, A and B, where this is the parallel. If this is R1 and this is R2, then it will be the parallel of R1 and R2.
So since there is the junction in between A and the branch are in between R1 and R2, it cannot be series, right?
Say that again?
So since there is a junction in between R1, R2, so let me just take my camera
Oh
on.
yeah, it's because we care about these two resistors. If they are in series, you will be doing a series from one point to the same point. That doesn't make sense. Your series needs to be between two different resistors. Like if I put a resistor right here, then this would be a different node. So now you have three nodes. So now I can say that R1 and R3 are in series because there is one single path from here to here. But once you simplify that series is going to be in parallel with this one right here.
So to be series, there should not be A on here and B. So those two branches should be removed so that it can be series, right? But since it has a branches here, it cannot be series, right?
Yes.
Okay.
And it's also the idea that kind of like when you think about the problem here, if you have a series from one point to the same point, that is useless. So a series that starts on one point and finish on the same node is just gonna be removed. But yeah, because that's why I like doing these extra lines right here, just to remind me and everyone else that when I have these lines right here, because of what you say, there is like a junction, I can go a different way than like they are being serious. But it's mostly a reminder. That's how I think about it.
Oh, okay, I understand. Yeah, thank you. Oh.
Someone is saying I was missing a resistor. That was intentional. I wasn't trying to solve the problem.
Yeah.
I just did a problem that was similar, but not the same, just to explain the idea of why we could remove this resistor here.
Okay, I got it. Yep, thank you.
Any other questions? Okay, I'm gonna be here for a few more minutes. If anybody has any questions, it's time. But I just wanna say thank you because you all were really talk active today, and I really appreciate it. And it just makes me happy, and I just wanna ask you to please keep doing that. This is a safe place for everyone, and like you are only get your questions answered if you ask questions. So just please keep coming and please keep asking a lot of questions. That way I know what you need help with, how can I help you, and we can work together. Okay? So just thank you. As I said, I'm gonna be here like 5 more minutes or so if anybody has more questions, but you're free to go now, and I'm also kind of stop this recording now.
Thank you.
No, thank you.
Thank you.
You're welcome.
Can I ask a real short question again?
Yeah.
Yeah, it's a problem 1. So I am not showing my answer. I just want to show how I, trying to simplify. Is it okay to share my screen? Yep. All right. So, yeah. So I'm trying to make it as a short circuit. So I left the current source here, and then I removed the voltage source. And then since there is a voltage passes here, so the voltage was in here, and then so I made it parallel, and then it goes like this, and then still the voltage flows in here, and then it's going to be series, and it makes like this, and then still it shows the voltage flows in this register, and it can be parallel, right?
Go back. How do you know from the first simplification to the second one? Why do you know that the voltage is still there?
I'm sorry.
When you did the first simplification, when you said they're in parallel, why do you know that the voltage is still there?
In this one, right?
In your middle circuit.
Oh, middle one. Hold on.
why do you know that on the middle one, the
Oh.
voltage is the same?
Oh, since it's series, it has a difference. It has different voltage, right?
Yeah, so what I was trying to get you to is when you did the first simplification, you told me, oh, they're in parallel, and then you draw it like that, right? And you told me the voltage is still here. That is true because when they are in parallel, components in parallel have the same voltage.
Okay.
So when you simplify, that is true, you still have the. Now, when you're gonna simplify, you have to be careful because if you simplify, they're not gonna have the same voltage anymore. Because components in
yes.
have the same current, they don't have the same voltage.
So in this case, I have to use the current division, right? To get, so since it's series in, hold on, I'm a little confused. So hold on.
There is different ways of doing it. So you can, it is not wrong to simplify to the next circuit.
To the next circuit,
yes,
like
it
this?
is not wrong. It is not wrong.
Okay.
What you need to know is that once you simplify, it is not true that the voltage across the 16/3 ohms resistor, that is not the same voltage that you are looking for. However, why is that helpful?
Hold on. Yeah, I understood. So series, they have different voltage, but simplify, I understand how to simplify it, but it has a different voltage. And then hold on. So I thought like in this in this between these two registers, they are in parallel, and then in parallel have a same voltage, and then something like that. But I think my idea was wrong.
I think you still can solve it, but yeah, you are missing like a part. Like go back to the original. What are you gonna say?
Yeah. So yeah. These two, even if they are in parallel, but as you said that we have a different voltage, and those two registers have a different voltage, right?
No, they will have the same voltage.
Oh, okay. I think I messed. I think I'm out.
Because you're getting confused, I will say don't think about the last one. Stick with the middle. Stick with the middle one.
Okay. Like
the middle one, how can you find the voltage across that resistor?
Hold on. In this one, right?
Yeah.
How can I find the voltage?
Actually, before you even do that, mark which resistor are you trying to find the voltage across?
I was going to find the voltage in this 10 register.
When you simplify it, where is the same voltage?
This here.
Yeah. So if you can simplify because they're in parallel, which means they have the same voltage. So after you simplify on that circuit, if you the voltage across, is that a 10/3?
This one, it's 2.
And the next one?
It's 12.
And the other one? 10/3?
3. Oh yeah, this one, yeah, it's 3, sorry.
10/3, right?
Yeah. So 10/3.
If you find the voltage across that 10/3 resistor,
okay,
the voltage across that 10/3 resistor is the same voltage as the 10 ohms resistor.
Nope, since it's in series, they both have the same voltage.
Yes. So you can just analyze this circuit and try to find the voltage across the 10/3 ohms resistor, and you will have voltage that you're looking for.
Oh, okay.
How can you find the voltage across that resistor?
I tried to hold on. So I tried before this one. Well, I volt hold on, current division.
If you do current division, you are finding a current. You are not finding voltage.
But
But if
since
you find current, how can you find the voltage?
so since I don't have a voltage source here, so since it's a current source, I was thinking that I had to use the current division. So V equals IR, and then I was going to multiply the current flow here and the voltage, no, the resistor, this one.
I think you may have the idea. So why don't you do it and then send me an email and we'll talk about it.
All right, yeah, sure. Okay.
Yeah, just make sure that you are finding the voltage across the 10/3 ohm resistor. That's
Okay.
also to remember. Don't forget that. That one is the one that you are finding the voltage across.
Okay. Yep. I'll try. Thank you.
Yeah, work on it and then we can talk about it.
All right. Yep. Thank you.
Yeah, no problem. Bye bye.
Thank you.
I just have a quick question about when things are in parallel, like in the first example, module 4, how do you know like where to put the like resulting resistor?
Well, it has to be between the same two nodes that the parallel was connected to, because parallel usually they're connected to the same two nodes. So the equivalent has to be connected between the same two nodes as well.
Okay, cool. That makes a lot more sense. Thank
you.
you.
When you talk about the series is the farthest away node.
Okay. Okay, cool. Yeah, I was working on the homework and I was like trying to figure out if I was putting like the parallel in the right spot.
Yeah, so always, that's why sometimes like, when I'm trying to do it slow, it's just that at the semester like keeps going, I try to go faster. So I don't like label all the things, but right. Yeah, like that's why at the beginning I was like coloring my notes and then being like, here's my pink node, like now the equivalent needs to be connected between pink and green, and so on. But yeah, everything is gonna build up on top of each other, so I have to like kind of like start going a little bit faster. But when you are doing it like at home, try to label the node like this is A and this is B, this is C. That way, when you are simplifying, that will help you make sure that you don't make a mistake.
Awesome, I'll do that. Thank you.
Yeah, no problem.
Professor, can I ask just one real last question?
No, go
yeah,
for it.
So in this case, can you see this? Yeah. So since there is no junction here, can those two registers be in series?
Yes.
Oh, okay. But combine these two and then it's gonna be the parallel with this one and this one, right?
Yeah.
I got the idea. Okay. Well, thank you.
No problem. Yeah, just look at it, and again, if you have any questions, you can send me email.
Right, yep, thank you so much.
Yeah, no problem.
Bye.
Bye. Do you have any questions? Just a computer that is on.